Hello everyone, today we are going to go through a topic called periodicity. So this chapter is basically understanding more about the period 3 as well as the group 2 and group 7 in chemistry. So without further ado, let's take a look together on the next page for the page of content. Alright, here so we are in the page of content. So there's a number of concepts in this chapter, but a lot of them are actually repeated based on the chapter on atomic structures, which is studying, the principal quantum shell, the size of ions, as well as the ionization energy. So the first two parts is more like a recap for you, which is concept number 1, concept number 2. Then after that, the brand new, something that is brand new in the chapter, we begin from concept number 3 onwards. As you can see, from concept number 3, we're going to study more about the trends in the melting and boiling points, the reaction of the elements in period 3, so on and so forth. So we will stretch all the way downwards to roughly around concept number 20. Okay, so concept number 20 is our target goal for today. So you'll find that the chapter here is actually very long. So what I suggest you is that after you finish the period 3 trend is basically end around concept 12, take a short break. Then after that, come back a little while, we go through continue with the video lesson with your group 2 chemistry. Then after which, take a short break. Then at the concept number 17, this is where you go to group 17. Okay, so this is like 3 different parts. Period 3, which is concept 1 to concept 12. Then concept number 13 to 16 is, or concept number 13 all the way to somewhere around 16 is more on group 17. Then concept number 17 stretch to 20 is more to group 17 chemistry. After which there will be summary and skill level practices. So without further ado, let's move together on the next page where we begin with the first part of period 3. Alright, so let's take a look at the first part. Now, the first part is like an introduction to you in terms of the periodic table. So take for example here, now we take a look at periodic table in a slightly different manner. Now, I know that most of you who are reading this chapter or reading this video lesson, you already have an understanding of periodic table. So I just highlight something for you. For example, in future, when people mention to you the S block element simply means it's group 1 and group 2 matter because it's written in NS1 and NS2. Then if someone tell you it's group or period D or your group D elements, this is basically your transition matter because the transition matter basically flew from the D electrons. Then they talk about the P block element. The P block element simply start from group 13 all the way to group 18. Why? Because you start to fill electron from the MP1, MP2, MP3, 4, 5, and 6. So this is basically what is the S block, the D block, as well as the P block element. Of course, here's the F block. This is a lanthanide. This is rare earth matter. Not really in our syllabus, but it's good to know. So this is all you need to know for this particular page. And the explanation is already written down here below for you. And this part is not so important. It's more or less like a review for you for the whole of periodic table. So let's move on to the next page where we study more carefully on our first concept. Okay, let's take a look at concept number 1. Now, concept number 1 is basically something you have studied before in the chapter on atomic structures. So let's take a look. Now, the first part we talk about the atomic size and the ionic size of period 3. Now, what I want you to do is I want you to focus your attention on this part, which is the size of your atom. Okay, this is the size of atom. Atom is different from ion. Atom itself. Now, what do you notice here? This is period 3. Okay, period 3. That means we're going across the period. Generally, the size of the element, you see that it decreases down the group. Why it decreases? Not say down the group, decreases across the period. Why it decreases? We need to use one formula to understand this trend. It is called effective nuclear charge is equals to nuclear charge minus away shielding effect. So your nuclear charge represents the number of protons. Then the shielding effect represents the electronic repulsion effect. So let me write down. It's called electronic repulsion. Now, what do I mean by electronic repulsion? So let me give you an example. So take for example here, you have an atom. This is the proton, and this is your electron. So this is one electron or one principal quantum shell. This is another electron or another principal quantum shell. You see these two? They are like repelling one another. This repelling is called the shielding effect. So there's a saying, as you go across the period, the nuclear charge actually increases. But at the same time, the shielding effect remains almost constant. Okay, almost constant. Now, why would we say the word almost? Because when you go across the period, electron increases, actually shielding effect increases because there is more repulsion, it's add more electrons. But they do a statistical calculation. They found that the repulsion is not very significant, hence they say it's almost constant. Then as a result, think mathematically, if your nuclear charge increase, the shielding effect is about the same. What happened to effective nuclear charge? Increases. And what is effective nuclear charge? The overall attractive forces. That means how strong the electron on the outermost quantum shell is attracted towards your nucleus, which is the proton. So the stronger it attract, the closer it pull towards. Hence the size decrease across the period. So that is our first explanation. And you can take a look at the keywords here, which is focused on the left hand side of the screen. Now, you see this is one whole bunch of keywords here. So no, we are not really going to memorize it like that. It's a bit too crazy. So what you need to do is you need to make full use of the equation that I highlighted above, which is the first one. Talk about the nuclear charge. What happened as you go across the period, the nuclear charge, which is the number of protons, increases. This is a keyword. The proton increases. Second, shielding effect remain almost constant. Okay, very important, almost constant. As a result, what will happen to your effective nuclear charge? Increases. That's what you say here. The effective nuclear charge increases. Then because you have more attractions, and that's the reason why there's stronger electronic attraction between the nucleus and the valence electrons. So there's a decrease in size of electron count. Hence, atomic radius decreases. So this is a typical 3 marks question, and that's how you explain it using mathematical equation. Now let's take a look at the next concept. So the next concept we talk about is ionic radius. So ionic radius, the difference is the matter loses electron, the non-matter gain electrons. So let's observe together this part here. The electronic configuration is written as 3s1. Now let's take a look at Na. What do you notice here? The difference in electronic configuration. This is 2s2 to p6. Oh, there's a difference. And the difference is one principal quantum shell. You see, this is 2, this is 3. So that explains why the size on top is bigger for atom. Ionic is much smaller because you have one less principal quantum shell. Similarly, as you go across the period, what happened to the number of proton? Increases. But you must not forget one thing. All the configuration you see here are the same. They have the same electronic configuration because group 1 lose 1 electron, group 2 lose 2 electrons, group 3 lose 3 electrons, so on and so forth. So all of them will have the same noble gas configuration. Hence, they are the same. Now, if they have the same electronic configuration, what is the consequences? Shielding effect now is not almost the same. It is the same. There's a difference here. So it's not almost constant. It's same right now for ionic. So which is why they're the same. What nuclear charge increases, what happens to effective nuclear charge? Increases. So stronger attractions. Second, if you go up to the n ionic radius, how come the n ionic radius is much bigger than the atomic radius? So to understand this, you must write down the configuration. So this is the configuration. This is 3s2 3p3. Now take a look at this one. 3s2 3p6. Wow, there's an increase in number of electrons. But how come if there's an increase in the number of electrons, the size increases? Well, there's a reason behind it. So this is what I'm going to do. We're going to draw an arrow here. So just imagine that currently you have a proton in the center, then this is the electron. Now we're going to draw another quantum shell, so you put one more electron. Now, what I'm going to do is I'm going to introduce more electron, because if you gain electron, there will be more electron. So just imagine that I'm going to add in one electron here. Now, what is the effect here? This electron is negative in charge. This is also negative in charge. What will happen when both negative in charge come into close proximity? They will repel. So they repel, what happened? It expands in size, expanding electron cloud. So that's why the size jump up. So the size increases. But at the same time, you must not forget, all of them are the same number of electrons, because your group 15 gain 3 electrons, group 16 gain 2, group 17 gain 1. So basically they have the same electronic configuration, and we call this configuration as isoelectronic. The same also apply to this, isoelectronic. Same number of electrons. So that means the nuclear charge going across the period increases, shielding effect is is constant, because same for ionic. As a result, decreasing ionic radii. But you must keep in mind, atom is much smaller than your anionic radii, because there's the expansion of the electron cloud due to the inter-electronic repulsion. So let's take a look at the keywords together. How do we put properly in words? So the first thing that you must say is, the cation is definitely smaller. Why? Because same nuclear charge, it has one less principal quantum shell, like what we explained. For example here, this one is like 3s1, this is 2s2, 2p6. They one less principal quantum shell, much lesser. So with the increased number of protons and the decreased number of electrons, stronger electrostatic attraction, decreasing size. What about anion? This is much bigger in size, because nuclear charge is the same. You have more electron. Remember the pictures? I say I put more electron inside. They will experience electron repulsion. Then as a result, there will be lesser attractions, so size increases. Then how do we talk about the trend across the cation and anion? Remember, it decreases across. So we say that the nuclear charge increases. Of course, going across the period, nuclear charge increases. But this time around, shielding effect is the same. Effective nuclear charge increases, so stronger attraction, decreasing electron count. And the same also apply for your cation and anion. Alright, so this basically wrap up the size of the atom and your ion. And let's move on to the next page. So we come into concept number 2. Concept number 2 is basically more talking about ionization energy. And this part is not very difficult. Follow me closely. We're going to use the same strategy to talk about effective nuclear charge. So effective nuclear charge equals to nuclear charge minus shielding effect. But you must recall, what is the meaning of ionization energy? Ionization energy simply means that the amount of energy to remove one valence electron in a gaseous state. That's what simply means. So as you know, going across the period, the proton increases. From here to here, proton increases. So let me put a note here. Proton increases. But what can you say about the shielding effect? Almost the same. So almost the same. So if you're almost the same, what will happen to the effective nuclear charge, which is the attraction effect to the valence electron? It will increase. So if there's increasing attractions, that is why generally you need more energy to remove the electron as you go across the period. Does that make sense to you? Stronger attraction, harder to remove. Then here comes the next part. Hey, you notice that there's two weird trends here. One is happened between group 2 and group 13. The other one is group 15 and group 16. So, how come there's a decrease in energy? Very simple. First thing, your Mg is 3s2 and your aluminium is 3s2, 3p1. So what do you notice here? There is one more electron. But the electrons for your P is of a higher energy than the S. So if you have higher energy, you need less energy to remove it. It's because it's further away from the electron. That is why, or further away from the proton. That's why weaker attraction, easier to remove. So they see there's a drop in energy. Then you move on to this one. This guy here, how come there's a drop in energy? Well, very simple, different reasoning, use a different color. So this one is 3p3. This guy here is 3p4. So what is so special about 3p4? So you see, you draw a structure of 3p4. This is how it looks like. So this 3p4 here has a packed electron, causes inter-electron repulsion effect. So hence, less energy required to remove this electron. So that's why you see there's a drop. That's how the reason why there's a drop in energy, so on and so forth. So how do we put this properly in words? We're going to use the same strategy as this one as well. So first thing first, talk about the trend first. The trend generally increases. That's why we say generally increases, because nuclear charge increases, shielding effect approximately constant, effective nuclear charge increases. Then as a result, you will have stronger electrostatic attraction, it increases. So you need more energy to remove it. So hence ionization energy increases. But you must not forget the anomaly. So the first anomaly we talk about is your Mg to Al, 3s2, 3p1. Your 3p1 is a higher energy than the 3s, so less energy required to remove the 3p electron in Al than the 3s electrons. Then what about the group 15 and 16? Because this guy here has a packed electron. So inter-electron repulsion, less energy to remove the 3p electron. So ionization energy decreases. Okay, so that is the main reason for ionization energy. Let's take a look on the right hand side. So the right hand side is about electronegativity. So electronegativity, right, I need you to put a star on this definition. This definition is very, very critical. It is asked very frequently in exam. So let's take a look very carefully what the definition is all about. It is defined by the tendency of an atom to attract a bonding pair of electrons. Can you highlight the word bonding pair? Now, bonding pair is very, very important because we talk about the bonding electron being attracted. Not any electron is bonding electron. So I'll give you an example, like HCl. The electron is bonded in the center. This is called bonding electron. So which means they only attract this bonding electron. Now, as you know, your Cl is more electronegative than your H in this case. So you will attract the bonding electron closer to the Cl. That is how it works. Now we move on to more things about electronegativity. So electronegativity, you must make note of one point. Your effective nuclear charge is directly proportional to electronegativity. Okay, they have a direct proportional relationship, which means effective nuclear charge increases, electronegativity also increases. It becomes more and more attractive, which makes sense because you have more proton, you attract the electron much stronger. So that is your electronegativity. Okay, make sure you're using effective nuclear charge to explain. So that is the first part, to wrap up all the things that you learn in atomic structures. So when you're ready, can you move on to the next page? Try out the 2 checkpoints. So give yourself time yourself about 2 to 3 minutes like that. After you're finished already, then you can check the answer. So make sure you put a pause on this video before you move on. Okay, I hope you have paused the video and tried out the questions. So let's take a look together. Now, the first question is about the variation of the radii going across the period. So you pay attention that this is the anion. This is 15, 16, 17. Generally decreases because we make use of one formula. Your effective nuclear charge is equal to Z minus shielding effect. Generally, it should decrease from here to here. Then at the same time, argon is noble gas, about the same size as chloride, but potassium is much lower. Why potassium is much lower? Because potassium has a configuration of 2s2, 2p6. And all this configuration here is having your 3s2, 3p6. So what do you notice here? Your potassium has one less principal quantum sharp, so it's much lesser. Let's take a look further on the next questions. So the next question is about the first ionization energy trend. So in general, you must know one thing, the ionization energy will increase across the period. And the reason is due to your effective nuclear charge again. Your effective nuclear charge equals to nuclear charge minus shielding effect. It increases about the same, effective nuclear charge increases. But there are 2 anomaly. The anomaly appear here and here. You remember this one is what? This one is your 2p1. So keep in mind, this one not 2p1, sorry, this is 3p1, higher energy. This one is what? 3p4, inter-electronic repulsion effect, so less energy required to remove it. Alright, so this is basically the 2 key checkpoints just to double check your understanding. So all the questions here are extracted from examination, so make sure do attempt it before you move on. This is to ensure that you really understand the concept. Once you're ready, let's move on to the real meat of periodicity. This is where we study something brand new on period 3 element. So let's take a look.